This is Ian Johnson's thesis defense here. He joined the program in Aeronautics and Astronautics in 2009, I believe. He then did his MS within our fan propulsion group here in 2011, and then continued on to do his PhD, which he is now going to tell us about. Ground rules are, if you have a burning question, then please do ask it, but unless it's a burning question, save it to the end of the presentation. Then we'll open up the general floor for questions, and then after that we'll ask the general audience to leave and let the committee continue its questioning. Faculty are, of course, invited to stay if they're so inclined during the examination part. Take it away, Ian.
Thanks, Robert. Thank you all for being here, especially so early in the morning. I think we should have got a bigger room. I'd like to talk to you guys today about one of the oldest electric propulsion thrusters, pulse plasma thrusters, and some of the new applications that we've been using them with over the last few years. The thing about pulse plasma thrusters, or PPTs, is they're unique in the fact that they have a wide regime where they can operate at, from pressure, energy, power, frequency, the fuel type that we put in, and we're going to talk a little bit about all of those. The first application, which is the oddball of the three, is air breathing, or a stratospheric airship. It's drastically less expensive to put an object up at 20 or 30 miles compared to a satellite up at 300 or 400. But up at that altitude, you can still get a large spatial area of coverage on the ground, a few hundred square miles. And so communication, data transfer, the internet, surveillance, camera operations for vastly less money, orders of magnitude less money than satellites. And up at that area, the wind force on one of these airships is less than 10 millinewtons. Usually it's more like 1 or 2. The second application is much higher power, where we integrated the pulse plasma thruster with the high-powered helican. And if you want to explore the solar system, you really need some type of high-power device. If you want to go to the sun or to Mars, you're talking about distances of 10 to the 11 meters. If you want to go out to the edge of the solar system, now we're talking 10 to the 13 meters, and then out to the Oort cloud, where there's asteroids from the very beginning of the start of things. Now we're talking 10 to the 14 meters, and you need much higher power to get there. And then the third regime is very low power. This is going to be small, low Earth orbit satellites, maybe things to go to the moon, satellites that only are designed to last for a couple of weeks or a couple of months. And these very small length scales, and you need very small changes in speed for attitude control, formation flying, some small orbit raising, things like that. So this talk will be a continuation of what I presented at my general exam, which was a little over a year ago. For the air-breathing atmospheric operation, we developed an in-air pulse plasma thruster. We characterized the thrust. We found that it was higher with the pressure, the cross-sectional area of the PPT, and then the energy that we fed into it. For the high-power device, we integrated the pulse plasma thruster with the high-powered helican, and that was with the old system, what Race got his PhD on, the 37 kilowatt helican. And then we completely broke apart that system and rebuilt it. And then for the low power, we tested sulfur and bismuth sulfide as thruster propellants. Since then, and what I'll be talking about today, for the air breathing, we flew an optimized area pulse plasma thruster, which was 4 times as large as the previous thruster we flew, but still small enough that we could fire at 40 to 30 torr. And we also flew it on a semi-rigid airship. As you'll see in the video, it was originally going to be a rigid airship, and then going through the jet stream, it became a semi-rigid airship. For the high power, we tested Teflon propellant with the 125 kilowatt helican, and we'll characterize and we'll show what some of those results are. For the low power, and this is where the majority of my work has been, we tested 10 different pulse plasma thruster propellants. We developed a first-order empirical equation to describe their performance and suggest some future propellants to attempt. And then I believe we started the CubeSat program here at the UW, and I built a 2 joule sulfur pulse plasma thruster and tested that in the lab. Right, so for starters, a little bit about the pulse plasma thruster. It's an incredibly small, simple device. We printed up a 3D mock-up of one, and I'll pass this around. If you drop this, it's okay. We've dropped it off a building before. There's no real damage to it. The PPT is incredibly straightforward. From a hardware standpoint, there's 2 electrodes and a fuel block in the middle. We short circuit the electrodes with the igniter discharge that allows the main discharge to flow. Few kiloamps of current. We get up to a few EV temperature that ablates the solid material, turns it into a gas, ionizes some of it, and then accelerates the plasma out at 20 to 30 kilometers per second based on what the fuel cell is. The main acceleration force for plasma is the J cross B, so you have a radial current and an azimuthal magnetic field, and right-hand rule, if you remember high school physics, that'll accelerate particles outward. And then neutral forces, we have a large pressure gradient built up by the electron-neutral heating. And it's small enough to fit in your hand, and there's a little picture, adorable picture of it firing in the vacuum chamber. All right, so we're going to start off with the air breathing, and then we'll move on to the other 2. So at the general exam, we saw that the impulse increased with pressure, area, and energy. However, the specific thrust, which is a term we'll be using a lot today, it's typically defined as the thrust out over the power in. So it's how efficient the thruster is. And that has units of newtons over watts. And that's unit equivalent to impulse over the discharge energy, which is millinewton seconds over joules. And that scales as the pressure times the area, and then the more energy we put in, the less efficient it becomes. We flew a single burst balloon. You can see in the center, went up to 105,000 feet, popped, came back down. Fairly successful. We found the balloon again, which is something I used to take for granted, and now after running a number of these balloon experiments with the ESS department, I no longer take for granted. And then we flew an in-air thruster design, which was a 1-inch diameter PPT with a 1/4-inch long cathode, and a couple pictures of the Grant County International Airport, and then up at 105,000 feet just after the balloon popped. So our goal has been to work towards, well, the goal is to build a long-duration stratospheric airship that can station keep, meaning it can maintain its position at an altitude of 100,000 feet or a little over 20 miles. And we took a large step forward from the single burst balloon. This was about a month and a half ago, where we built a semi-rigid airship. It was made out of carbon fiber rods, 3D printed components here on campus to connect everything, and then a whole lot of epoxy to hold it all together. More epoxy added the morning of the flight. And we had multiple balloons to make it more of an airship design, and this is all moving us towards a Zeppelin concept that can stay up at altitude for longer. We had to drastically increase the computer, the microprocessor that we had from the 2013 flight, as we wanted the capabilities to be much, much higher. So we custom made a board that had GPS, onboard data storage, a radio, 144 megahertz to transmit back where it was. And then we also made a 5-centimeter diameter pulse plasma thruster, which you can see in the lower left. Much larger, much larger performance and much louder when we fired it in the bell jar in the lab. So I think I have a 1.5-minute video. See if this works, and I'll narrate this. So this is Robert, who you can hear laughing or crying. I'm not sure which. And this was the onboard video camera. So we're looking, we're about 1 meter down, looking directly at the thruster. And a nice smooth flight for the first 10 minutes. And then we hit the jet stream, which was moving at around 200 kilometers per hour. And things got a little out of hand. This was more force than we were expecting, but we were very pleased that the structure held together going through this, which was much stronger winds than we were expecting. And then up at altitude, even on one of the strongest days of wind that we'll see, very calm up top. Very, very calm. So about 10 millinewtons of force if we had a long body Zeppelin airship. And then you can see the little flash and hear the PPT when it fires. We were designing to have a frequency of, firing once every 4 seconds. And then that varied between 4 and 15 seconds. And then same as before, when the balloon pops, everything then breaks on its way back down. We launched from Moses Lake, which is in the middle of the state, and it traveled south about little over 100 miles and landed 10 kilometers northwest of Walla Walla. And that was a long day to find. I think this is my favorite picture from the whole thing as it's falling back down to Earth. So just a little bit of the performance. We fired at pressures between 20 and 15 torr. At fairly low energies, we were being pretty conservative with this flight, between 6 and 32 joules. We had an impulse varying between 1 and 3 millinewton seconds. And we currently, in the lab, have the electronics capability to fire at 10 hertz. So this puts us well over the 10 millinewton thrust range that we need to overcome the drag force. And then the specific thrust varied from about 120 millinewtons per kilowatt down to 100. And even though we're firing in the atmosphere, current day electric propulsion, Hall thrusters, well-optimized ion thrusters have an efficiency of around 40 millinewtons per kilowatt. So without doing all that much work, we're already have a specific thrust 3 times as high as the most efficient in-space Hall and ion thrusters. Thrusters, which I should add, can't operate in the atmosphere because of the high pressure background. So moving on to our second area of focus with the high-powered Helican, which is a project that is what started the lab. It was a solar wind source, and that transitioned to a thruster in its own right. And then I've been looking at integrating the solid fuel, and we're also looking at firing 2 or more of them together at the same time. So we wanted to replace the gaseous fuel system on the Helican, and there's a number of reasons to do that. The primary one is solid. A solid propellant has a much higher storage density than a gas or liquid does, meaning for a given volume, you can simply have more mass. And more mass means you can go further and you can go faster through the solar system. Also, it removes any complex and heavy tubing, tanks, valves, which also allows the ability for very discrete pulses. And when you're firing inside of a metal vacuum chamber, to remove wall effects from the equation, you need very, very short pulses so that the electrons don't have time to fire, hit the wall, and travel back into the source region. So a little bit about the thruster. The Helican is a unique device in that we can get typically order of magnitude higher plasma densities than comparable power level EP devices. We create an electromagnetic wave where the wave number is parallel to the base field, and we operate the antenna at around 1 megahertz, which is much higher than the 100 kilohertz ion cyclotron frequency and much lower than the gigahertz electron cyclotron frequency and the terahertz plasma frequency. The antenna creates a radial electric and magnetic field, which then couple into the wave and propagate through the plasma downstream. It's very effective at accelerating electrons while leaving the ions fairly motionless in the source region. So we accelerate the electrons out. That builds up a large E field that we call an ambipolar field, and that field then pulls the ions with it downstream. So in that regard, it's typically thought of as an electromagnetic thruster in that it electromagnetically accelerates the electrons, but you could also consider it an electrostatic thruster in that we're accelerating the ions with an E field. So I was saying we do this with a 125 kilowatt tank circuit, which is more or less, we have 2 switches and we operate them out of phase, and they create this nice sine wave that extends for as long as we'd like it to. That's the blue trace you can see in the figure. And then when we load the antenna, which you can think of as adding a secondary to a transformer with the pulse plasma thruster creating plasma. So the PPT current pulse is here in this lime green color that MATLAB seems to be a huge fan of. So that then loads, it puts a load in the antenna, which then decreases the current, and you can see that in red. So the antenna is shown in the top, top right, attached to the vacuum chamber in the middle, and then our electronics, which a company in downtown Seattle, Eagle Harbor Technologies, helped build for us. So really I'm just showing this slide because I like the pictures. I think they look really cool. But we need a base field for this helican to operate, and we do that with two different systems. We have 6 coils that produce the field in the source region that you can see here. We get around 800 Gauss in the source region, and that extends is above 0.5 Gauss for 3 meters, which is the length of the chamber, and 0.5 Gauss is the Earth field strength at this latitude. So we're above that for the entire length of the chamber. And then we can also add 2 downstream antennas that you can see in the lower right, and that extends the field out to 4 meters and increases the field downstream, which helps keep the electrons magnetized as well as flowing in that ambipolar field. So back at the general exam, we fired the PPT with the 37 kilowatt system, and we got the red trace, which we got a very high plasma density, but it doesn't last for very long. We simply ran out of materials compared to the gas device, which is shown in blue, where you have a slightly lower plasma density, but it's a longer pulse, so we end up with higher thrust out of the system. And so what we suggested doing was we need to increase the amount of mass that we're ablating from the pulse plasma thruster. And as we know that the thruster current scales as the energy in amplitude and then the inductance in the period, or how long it's oscillating for, we suggested raising each of these, and I'll show you a few results of that. First, with the inductance. So typically the pulse plasma thruster has a stray inductance of around a microhenry or so. So we increased that to 5 microhenries with a coil. And that trace is shown in red, and then if we don't add any material, that trace is shown in blue. So with the 0 microhenry case, as expected, we have a higher peak density, but when we add the 5 microhenries of inductance, now we get a longer curve, and so we actually have a larger total plasma flux coming out. When we fire it with the pulse plasma thruster, we see something different, in that the 0 microhenry case, we get the higher peak density, and we also get higher plasma flux, implying that this was a waste of 6 months of my life. We can also see the same thing in the pressure, in that even though we're getting more plasma flux coming from the 5 microhenry case, the 0 microhenry case, we get a higher pressure increase in the chamber, meaning we have more particles coming out, suggesting that we have more neutral particles coming out, which implies that the helican is operating on those neutrals that the PPT is creating. And then when we fire the device with the helican, we see a much larger pressure increase in the chamber, meaning that we're creating more particles with the HPH system. And so the helican is ablating more particles than just the PPT alone. And our assumption for that is that we have this base magnetic field where the electrons are gyrating around the field lines, as well as being accelerated out and then slamming back into the source region. So we have a lot more electron collisions that are going to ablate more particles and turn more of that into plasma. So the inductance didn't work out. The next thought was increasing the discharge energy, and this worked quite well. So both of these plots have discharge energy on the x-axis. Top one is density, particles per meter cubed on the y-axis, and the bottom one is the chamber pressure increase. So just the PPT alone, we have downstream densities of 10 to the 16 particles per meter cubed. And then as we start to add in the components, we see that increase. So with just the antenna, there's not a whole lot happening. The antenna needs that base field to operate. The PPT and the base field alone, which is shown in red, we have about an order of magnitude increase in plasma density. And then when we add the antenna and the base field, now we get about a doubling of the plasma density, as well as the neutral pressure in the chamber from just having the base field with the PPT. And so this implies that the antenna, which we knew already, requires the field to operate, or it's completely useless, just a waste of energy. And then we also see that the HPH is ablating around 5 times as much mass from the pulse plasma thruster as it is alone. So comparing our pressure input from the PPT and the Helican to what we usually operate with the gas system, which has been argon recently. We've also fired with hydrogen and helium. We want to increase the exhaust velocity. So this is simply shot time and then pressure change on the y-axis. So the PPT, we have around a 2 microtorr pressure increase in the chamber. The solid fuel HPH is 10 microtorr. And then when we fire with the argon gas, we have around a 400 microtorr increase in the background chamber pressure. And so we have around 100 times lower mass with the solid fuel system as we do with the pulsed version of the high-powered Helican with gas. And the reason for that is that the gas moves relatively slowly, especially at first. And so we have to puff in quite a bit of gas before we fill up that antenna with enough for the ignition to break down and for the Helican to actually operate. And so we have a lot of wasted gas that we input before, and then because those valves don't move all that quickly, the gas trails off after the discharges happen. So there's a lot of excess gas before and after that with the Helican system we don't have. And so we'd make the claim that the solid fuel is raising the mass efficiency of the high-powered Helican for pulsed mode, and drastically, about 100 times. So we took impulse measurements using downstream thrust stand. This was a pendulum thrust stand, meaning we fired plasma at it. It swung backwards, and then using a displacement sensor, we were able to fit the distance that it moves to the generic oscillating harmonic oscillator equation. With the pulse plasma thruster, we got around 10 micronewton seconds of impulse that was imparted to the pendulum without the downstream nozzle, and then that got increased to around 25 micronewton seconds with the downstream nozzle. With the field, just as we saw large density and pressure increases, we see a large impulse increase, almost an order of magnitude. Again, the PPT and antenna, that's completely useless. And then when we add everything in together, we go from that 10 micronewton second pulse plasma thruster up to 195 micronewton seconds with the base field and antenna and downstream nozzle. So much higher displacement. So impulse imparted to the pendulum is great, but really we want to know what's the impulse that's coming from the thruster. And the proper way to do that is to mount the thruster onto a thrust stand itself and see how far the thruster moves. That's hard to do when the thruster is built into the chamber. We can't move the entire chamber. So we have to make some estimates. And we did that by taking radial cross-sectional profiles downstream, assuming concentric symmetry to the plasma, and then being able to determine what our radial flow is to see how much of it is hitting the 10 centimeter pendulum downstream. And so in that case, then the impulse from the thruster times the percent that's hitting the pendulum is simply going to be equal to the amount or the impulse that was imparted to the pendulum. So the pulse plasma thruster, we had around 1.5, an estimate of 1.5% of the plasma particles that imparted, which is slightly higher, but about what we expected for a thermally expanding plasma. For the Helican and the Helican with the downstream nozzles, we saw a much more collimated beam, which is also expected as the magnetic field should help confine those particles to the center line. And then the Helican wave, so we get a J cross B force that moves inward. And so that 1.5% gets increased to 4.5 with the Helican, and then increased slightly more when we add on the downstream nozzles. And so now we can look at what the impulse from the thruster and then the specific thrust of the entire device is. So we have our 10 micronewton seconds from the pendulum. We multiply that, or we divide that by 1.5%, and we come up with an estimate of 0.6 millinewton second impulse, which is on par for most 100 joule pulse plasma thrusters. We normalize that by the energy input, and we get about a 6 millinewton per kilowatt device, which is, again, on par with most pulse plasma thrusters. And then with the Helican, we have our 125 micronewton second. That gets increased to 2.7 millinewton seconds. When we add in all the energy from the base magnetic field nozzles and the downstream nozzles, our efficiency actually goes down. To create that large 800 Gauss field, that requires a whole lot of energy. And so our efficiency is down to 4.2 millinewtons per kilowatt. And then with the downstream nozzle, it goes down even further to 3.3. So we said, oh, that's not good. Is there any other options? And instead of an electromagnet where we're discharging a capacitor bank through these coils, we could use a permanent magnet similar to what might be on your kitchen fridge at home. And some ref estimates by Chen down at UCLA, who kind of started this whole HPH, or the Helican experiment. For our geometry, we could use magnets that weigh anywhere between 12 to 20 kilograms, which I'm the first to admit is fairly expensive from a mass standpoint, but it's not huge. But the great thing about this is that our 4.2 millinewtons per kilowatt goes up to 16.9, and then if we include the downstream nozzles, now we have an efficiency of 23.8. And as I was saying earlier, the optimized, NASA's spent millions of dollars making these as good as they can be. Hall thrusters and ion thrusters are around 35 to 40 millinewtons per kilowatt. So now we're starting to come up to that range of what the best in the world can do. And so I would claim that we have a fairly high performance thruster with high mass efficiency, and by using solid propellant we have a very high storage density and a much less complex thruster than the gaseous version. So I think we've made a lot of progress here. And I'd say the next two kind of logical areas for improvement here, as the plasma density and pressure kept rising as we increased the energy on the PPT, I'd suggest we need to revamp the laboratory a little bit higher to go to higher. I think we were operating at 120 joules was the highest PPT discharge we went to. And let's see how high we can go up with that. And then start researching and looking at some permanent magnets to see how the efficiency changes with those compared to the electromagnets. So switching gears to our third regime of focus. So we were talking about 125 kilowatts for the high power. Think about a 60-watt light bulb at home. That's a lot of 60-watt light bulbs. Now we're going to drastically scale that down to 1 watt, 5 watts, 10 watts, depending on, but much lower energy than the light bulbs or my computer is taking up right now. So being in the Earth and Space Science department for our lab, we had a lot of people who say, hey, I found this cool dirt. Can you guys try firing that? And I'm like, no, I want to graduate. But we did test 10 different propellants. And our thought process was, just as if you took a plane flight from Seattle to, say, Sweden, it wouldn't make sense to carry the propellant for the return trip on the way out there. You'd want to refuel once you're in Europe. And so if we had a mission to the asteroid belt or to a moon or some other object, the cost and the weight of these satellites just dramatically increases because we don't have the ability to refuel there, mainly because these Hall and ion thrusters require a very specific type of gas. Usually they run on xenon or krypton, which is not easily found out in the solar system. And the great thing about the pulse Wowsen thruster is it doesn't really care what you put inside of it. It'll ablate it and it'll ionize it and eject it out the back. And so we tested a number of minerals. Chalcopyrite was one of my favorite. It's fool's gold, so it's this sparkly thing, and I feel really rich when I have it in the lab. We tested bismuth sulfide, olivine, which is one of the most common minerals on Earth. It has that greenish hue to it, as well as volcanic ash from an experiment volcano down in South America, and then sulfur, which we'll see had the highest performance. We also tested a few metals. Thought process here, there's a lot, space debris in our lifetimes is going to be a huge issue, and every kind of reasonable option that I would claim is not. We send up a mission, it grabs one piece, it deorbits it, and then the mission's over because it runs out of fuel. And however many millions or billions of pieces up there, that's not a feasible plan moving forward. So we need a system that can latch on to a satellite, refuel at that satellite, deorbit that component, and then move on to the next one. And if we can use some of that satellite as propellant in the thruster, we could, in theory, operate forever. And so looking at trying to fire with metals that spacecraft are built out of, or circuit boards or little electronic components. So we tested lead, bismuth, and gallium. Gallium's really fun because the melting point of it is around 85 degrees Fahrenheit, which is colder than your body temperature. So you can hold it in your hand and see it melt right in front of you. And then we also tested Teflon, which is the standard, and epoxy as a baseline. So we can see the thruster firing in the chamber. We built a small little thrust stand to fit in our small bell jar. And then these were just 6 of our propellant fuel cells that we made up. All of them used a Teflon insulator around the anode and the cathode, and that was necessary especially for the metallic fuels, which simply short-circuited out the main discharge without those. And so for all of our minerals and metals, we use that Teflon to make it the same between all 10. So this graph is showing the measured impulse from the thrust stand versus the main discharge energy. And Teflon, or the baseline, the standard that's been used, is down here in these blue circles. It's near the bottom. Just about everything we fired had equivalent impulse or higher. Sulfur in the red circles, much higher than everything else. And you might also notice that bismuth sulfide and yeah, I think it's off a little bit. Bismuth sulfide and chalcopyrite, which both have sulfur components inside of them, were the next highest.
Not olivine at the top?
No, I do not believe that is olivine at the top.
Too bad.
Wonder why I put epoxy down low. Yeah, sulfur's at the top, and then bismuth sulfide and chalcopyrite are the next 2 down. And both of those have sulfur components inside them. So there's something about the sulfur that seems promising. And then, so sulfur being the highest performance, and then that the PPT can operate on whatever you put into it, are the 2 big takeaways from this graph. So we said, all right, so we have all these propellants and we have this data. Is there some way to make an estimate for what the expected impulse should be based on the chemical properties of these propellants? And this is a process that you could go down the rabbit hole really far with, and we decided to do a first order analysis where we only looked at these 5 components. So the discharge energy, the enthalpy of sublimation, which is the energy required to go from a solid to a gas, the energy required to strip an electron off of a gas molecule, so the energy required to go from a gas to a plasma, the atomic mass of the particle, and then the species fraction. So something like Teflon, which is C2F4, we assumed it's going to be 33% carbon and 66% fluorine. And after numerous undergrad hours playing around with different forms of this equation, numerous possibly being an understatement on that, the equation that we came up with is up here. So we simply said the impulse bit is going to be equal to a constant multiplied by energy raised to power beta times the sublimation enthalpy raised to a power, the ionization energy raised to a power, and then the ion mass raised to a power. And after more numerous hours by the undergrads playing around to find where we can maximize these curves to fit the performance of the 10 thrusters, or the 10 propellants that we tested. These are the constants that we came up with. And as expected, the power on the sublimation enthalpy and the ionization enthalpy were both negative, which makes sense as we go to lower energy to go from a solid to a plasma, we should get higher performance out. The atomic mass was only slightly relevant to this equation, and then the energy scaled relatively linearly. All right, so the result from this, I've only plotted 6 of these, but when we compared the experimental results to what we found with this equation, things matched up pretty well. We had a coefficient of determination for Teflon and epoxy, both above 95%. Sulfur, olivine, volcanic ash, bismuth sulfide. Everything turned out well. Where things went off the rails was for the metals. Gallium and then lead as well, which I'm not showing on here. We both only matched around 50%. And some interesting things happened when we fired the metals is that we got a lot of macroparticles being ejected off, as well as we ended up short-circuiting the electrodes after a few hundred shots. And what that implies to us is that we were redepositing a lot of material back onto the electrode. So something was happening with these metallic fuels, especially at the higher discharge energies, that wasn't happening with the rest. So there's some second-order effect going on there. But for all the plastics and the minerals, this equation matched very, very well. So this led us to wonder, are there any other elements that can outperform sulfur? And so this graph is showing our expected impulse bit based on the last equation versus the discharge energy. So this is for Teflon and sulfur. And playing around with every element in the periodic table, except for some of the strongly radioactive ones down low. Slightly radioactive was fine. We found 3 that are expected to outperform sulfur. Cesium, rubidium, and potassium, with cesium being the highest. Potassium, slightly radioactive. It's in bananas. Rubidium, no one uses rubidium. Cesium was most interesting. There was some research done with cesium at the Glenn Research Center back in the 50s and 60s, as well as it's been used in some arc jets recently. And cesium is also slightly radioactive. And knowing my advisor, I can't decide if that makes me really happy I'm about to leave the lab or really sad that I'm about to leave the lab. But we'll see how that goes. But cesium should be expected about 25% higher thrust output than sulfur.
You have to be careful handling that.
Yeah, so the issue at the Glenn Research Center was they ended up, the melting point of it is also very low. So they ended up with pools of liquid radioactive material at the bottom of the vacuum chamber. But, you know, if you get higher thrust, who cares about that?
I did not teach you.
Liar. So the other low power system that we were looking at was a CubeSat, and I have a mock-up here that we put together. And unlike the 3D printed PPT, don't drop this one on the ground, but you guys are welcome to pass this around. CubeSats were developed down at Cal Poly in Stanford in mid-1990s, early 2000s, and they were specifically designed for university laboratories to be able to give low budget, low personnel, low knowledge people the ability to put a spacecraft up in orbit. And these things are tiny. They can fit in the size of your hand. This is a 3U CubeSat, meaning it's 3 10 centimeter by 10 centimeter by 10 centimeter blocks stuck on top of each other. NASA launches them for free. If you're an entrepreneur and you want to launch one yourself, one of these will cost you about $300,000, which is a lot, but isn't that much in the grand scheme of things. So we started a CubeSat program here at the UW. I'm now phasing out. The grad students are Paige and Paul, who are running it from the ESS and physics departments. I specifically focused on the thruster subsystem. So we fired a 500 millijoule to 1.9 joule sulfur PPT. We built up the hardware and the electronics for that to fit inside of the CubeSat form factor, and then we also had an Arduino Uno computer for control. We also built up the other systems you need for autonomous testing in the laboratory, which you can see inside there. All of those now have been surpassed, and we're going bigger and better. But we are doing a lot of 3D printing on campus. This is a WindForm material. It's a company we partnered with on the East Coast. It's a carbon fiber composite. We've tested lithium ion and lithium poly batteries along with the solar panels to recharge them. And then the Arduino control, and then XB communicators to go along with that. And you might notice this one has a large empty section in the middle where we could put a payload or an octopus in this case, which you'll see when you get it. So to characterize the performance of the pulse plasma thruster, our thrust stand for the bell jar wasn't sensitive enough. Our data collection couldn't pick up how much it moved because we're at such low energy discharges with this PPT. And so we built a 5-prong double Langmuir probe array that we put in the plume downstream. So taking 5 measurements gave us the spatial distribution, and then we could assume what the cross-sectional is. And then the impulse is simply nm v squared at. So we were able to calculate that. And you can see the distributions form relatively nice Gaussian functions as the plume expands off axis. So with testing, we tested sulfur as well as Teflon, and just as with the higher energy discharges, we see that sulfur is about a 2 times performance increase over Teflon at these low energies, same as the high energies. Our specific thrust is a little bit lower at these low energies. I think sulfur was 25 to 30 millinewtons per kilowatt, and here is more 15 to 20 millinewtons per kilowatt. So the PPT becomes more efficient as you scale up the energy. And we do see the increasing specific thrust curves. If we compare this to the current state-of-the-art Teflon pulse plasma thrusters, which are currently designed by Clyde Space over in Europe, their Teflon thruster outperforms our Teflon thruster by a factor of about 1.8, but our sulfur thruster outperforms their thruster, so I'm holding on to that. However, if our doubling of performance by going from Teflon to sulfur transfers to the geometry that they have with their rectangular thruster, that should end up with specific thrusts of around 30 to 32 millinewtons per kilowatt. And then that's bumping up to that efficiency of the optimized Hall and ion thrusters. That ion thrusters certainly can't operate at these small sizes and low power levels. And Hall thrusters are just starting to be built for these CubeSats. Aerojet over in Redmond is doing a lot of work with that. So in summary, we worked on the pulse plasma thruster in a number of different regimes and energy levels. For atmospheric operation, characterized the thrust, and we flew 2 autonomous in-air tests moving us towards stratospheric airship. For the high-power Helican, we revamped the entire hardware and electronics setup to increase the antenna power by a factor of 3, and then we successfully operated a solid fuel, so we have higher storage density with the HPH and fairly high-performance thruster. For the low power, we tested some non-plastic propellants, which is the first time that's been done with PPTs, and then we also have started to build up a CubeSat program here at the UW. And so before I wrap it up, a few of us were counting the other day, and we may be off by a student or 2. Counting is difficult, but we're fairly confident that over the last few years, the work that I presented, we had 52 students in the laboratory from 12 different majors across campus. And that's a ton of people, all who added expertise that I didn't have, and they had to teach that to me. But for all these atmospheric flights, we required a whole host of people to build the balloons and the structure. And the CubeSat, with how many subsystems we've been working on, that requires just a ton of people to help us out on that. There's just so much to do to build one of these satellites. And so I'd really like to say thank you to all of you who are here and those who have helped us. It really wouldn't have happened without all of you guys working on this with us. So with that, I want to say thank you for waking up so early, especially those of you who usually sleep in until noon. Thank you for being here, and I will be happy to take any questions you may have.
So you had mentioned throughout the talk, particularly with the fuel research, the improved performance that you were seeing from sulfur over Teflon. Can you speak to particular operating environments where that fuel source might be appropriate and others?
Yeah. So Teflon is a very light propellant, meaning the exhaust velocity is going to be very high, 25 to 30 km per second, whereas Teflon's a little heavier, cesium heavier still. As we increase the atomic mass, the velocity is going to decrease by the same value. So if we're looking for a mission where we have a long period of time, a long time frame to make our orbit change, or we need to get up to very, very high speeds, going to an exhaust propellant that comes out at a higher speed is going to be much more effective. Where we need to change course dramatically, but we still need more propellant than what typical chemical propulsion systems can do. We want to go to a higher propellant where we can ablate it quickly, throw off as much mass as we can, and the slower it moves, well, throw off as much mass as we can so we get a very high acceleration change over a very short amount of time.
Yeah, I was curious. So you had a very complicated, someone else have a question?
We'll ask.
Yeah, I do.
Oh, from James.
Am I being received?
Yeah, yeah.
Okay, well, I wanted to follow up on the last one. And so imagine you're God for a moment, and you can design the perfect propellant for a given application.
Okay.
So never mind the periodic table or whatever. You know, this ideal propellant. Maybe call it Johnsonium Winglee or
It's such a Jim statement.
combination of ionization energies, mass, chemical bonds, anything.
Sure. Sure.
Make it up and put it together.
So the question is, what's the ideal propellant for a certain mission? And that entirely is going to depend on what the mission is. But my ideal propellant would be one that's very abundant and very cheap. Very inexpensive to get. If we want to travel a long distance, we need something that can get us the highest exhaust velocity possible. So that would imply we want low atomic mass particles. But if we want to get high thrust out, we need high atomic mass particles, which is why electric propulsion usually uses xenon or krypton. They're very low down on the periodic table. Some other things we want would be we want to ionize the particles. We need plasma, but typically it requires more energy to strip off 2 electrons than it requires, the energy input required to strip off 2 electrons is usually more than the extra kinetic energy we get from having a doubly ionized particle. So we'd like something that's very easy to ionize in its first state, but then its second energy level is very, very high. So we get a large population of singly ionized particles, and then nothing doubly or triple ionized.
Mass of helium, but the electron structure of xenon. Is that helpful? Or no?
So that would imply that we're going to have very light ions that are singly ionized, allowing us to get up to very high speeds, but our thrust is going to be fairly low. So that would be for a mission where we need to travel a long way, but we have decades to get there. What would be ideal for, I think, most missions where we have time-dependent time frames where we actually need to cover some distance quickly is going to be a particle very similar to xenon or krypton that's very heavy. The ionization structure allows us to get singly ionized particles, but it's also drastically cheaper than xenon or krypton, which the price of has been skyrocketing in recent years. If that is what you're looking for, Jim.
Yeah, so maybe it is the way around. So maybe we want something with the mass on but the electron structure of hydrogen, so there's just one electron we knock off easily.
Sure, and we're going to get the highest exhaust velocity possible from that, meaning in theory we're going to have the highest delta V imparted to the spacecraft.
Okay.
So which would be better? Hydrogen or tritium?
Now we're starting. See, I like CubeSats. I like CubeSats, and my little 10-watt thruster. We can't do a whole lot with tritium and your 100 kilowatt systems.
This is friendly tritium.
Friendly tritium, yeah. Friendly cesium that we're testing.
Optimize the ISP you want to run at.
So optimal ISP is an interesting concept. In theory, the perfect solution is to have the exhaust velocity, or the velocity of the exhaust be exactly matched to the velocity of the spacecraft. So you can think as the particles come out the back of the spacecraft to an observer that's in a different reference frame, you want the exhaust to look like it's not moving at all. Any extra kinetic energy in the exhaust is kinetic energy that's not being imparted to the spacecraft. So something that would be great for a pulse plasma thruster concept would be to start off with something like sulfur, which is quite heavy and moves relatively slowly, and then slowly fades into Teflon as you build up to high speeds, where then we're able to better match the exhaust velocity to the spacecraft. And that's somewhat commonly done in varying the power levels of electric propulsion systems. And then the best example is the space shuttle, which has the solid rocket boosters and the liquid propellant tank that has different atomic masses and therefore comes out at different speeds, and they match that to the speed of the shuttle. Race had a.
I had a question. So, you mentioned that there were a bunch of macro particles coming out of the switch metals. And I know the equation's already super complicated, but I was wondering if recombination of sort of like globbing stuff back together was in that equation, and that might help explain whether the macro particles are being knocked off as chunks, like it's finding features, or if it's like clouds of gaseous metal that are globbed together.
So that's something we've talked a lot about, because we're not seeing a buildup of solid material at the bottom of the vacuum chamber. But any of those large macro particles, so we're talking about things that are maybe the size of a grain of sand or half a grain of sand, so macro particle, any of those are going to come out very, very at a very low speed, maybe 500 meters per second, a kilometer per second at most, and that's fairly useless for getting any impulse out of the thruster. And so what we want is very, very small, ions that easily break off into a plasma and a gas. And some of that may be with how we built up the fuel cells, and there could be more work to be done there. But especially with the metals, where we saw that those large particles coming off, these large sparks on the high-speed camera, I think that's all just a loss for the pulse plasma thruster. And it makes sense that we have more of those as the energy was raised for the PPT, which is, I think, what we saw there.
Okay, don't hate me for this. But this just occurred to me. When you're talking about increasing the avoided mass using Panther with the solid fuel source, you base that off the pressure, right? Mm-hmm. And what are the chances that you're avoiding molecules and all the antenna is doing is allowing those molecules to break up further?
Sure. I think that is happening. Okay. I think it's a combination of the two. So we're getting the electron neutral collision frequency is going to drastically increase, and that's going to ionize any large molecules or macroparticles that come off, as well as ablate more gas in the first place. But I think typically those macroparticles occur later in time. I think the initial high current pulse is creating mostly plasma that's coming off. So I would make a guess that, well, the macroparticles are usually created hundreds of microseconds to milliseconds later in time.
Not just macroparticles, like, C2 or something.
Any gas?
Yeah,
part?
so what if you're taking...
Sure. I think so the PPT has an ionization fraction of around 10%, whereas Race's work on the Helican shows that we have an ionization fraction there of 90%. So I'd assume any of that neutral gas that we're creating with the PPT, the Helican is able to push it into a plasma. But either way, any gas that's created should be picked up on the pressure sensor. The only thing that the pressure sensor wouldn't pick up is any solid macroparticles that wouldn't reach the gauge. So I think we're either breaking apart those macroparticles into gaseous pieces, or we're simply creating more gas and plasma in the first place.
So on your various concepts, there's some couple of metrics that I didn't get. What about the actual overall efficiency of your PPT process? You mentioned 10% ionization for PPT. 90% agree on a combination of the two or not. And another metric is the specific power. So
Sure.
kilowatts per kilogram.
Yeah, absolutely. So my work only just started moving towards thrusters that we don't plug into the wall. And so for the CubeSat, we've looked at, it would take me a second to come up with the number in my head, but we've looked at our thrust out versus our power input. But for all the laboratory thrusters, we've just plugged those into the walls and haven't been overly concerned with the electrical efficiency of the system. But as we're switching to a constant current source for charging the CubeSat capacitors away from a constant voltage source, our electrical efficiency should go up. Well, it will go up as they're more efficient charging systems. So for the work that I've done, we really haven't been overly concerned with that. But I think as the CubeSat progresses further, that'll be a large feature. But either way, it's the same amount of energy in for Teflon or sulfur. And so if we have a ×2 thrust increase with our current system, we're going to have a ×2 specific power increase as well.
Yeah, I think the other metric that we've been concentrating is power per cubic meter. So at the moment, the push is to make sure it fits into the CubeSat. So the devices, both the electron as well as the PPT, allow us to minimize the space footprint of the devices relative to the other competitors. And that's what we're concentrating on.
So it's funny. Assuming I passed today, I have no problem putting junk in our vacuum chamber.
That's a long story.
Yesterday, I would have had a huge problem with that. But if we've had a huge increase with sulfur in the belt jar that we've just trashed and broken everything on and had to replace. I certainly now have no problem doing that exact same thing with the Helicon system, but the Helicon is simply too big to put in the belt jar. But that would be, I think, a large financial investment on our point, as the sulfur, Robert hates it when I say this, but the sulfur reacts with everything, and we use copper to make all of our vacuum seals, the ion gauges, RFAs, turbo pumps, all of those are going to be affected. Anything that has any carbon component, or anything that has any copper component in it, or let's be honest, sulfur reacts with everything. That's going to be an issue for the main chamber that we've tried to keep somewhat clean and been almost successful with that. But yeah, I'd love to know what that looks like.
What are your ISPs in seconds?
So yeah, so for the PPT, if we take, let's see, so we assume that the neutral gas was coming out at 500 meters per second, and for Teflon, we have an ISP of 350 seconds, and then sulfur, because although the plasma is coming out at a lower speed, we have a higher plasma fraction. That ISP goes up to around 385. We have to make estimates for the neutral velocity for those, so those are going to be rough numbers. But 500 meters per second should be fairly close to what we have.